This course module covers the basic technical principles of these swirl flow meters. After completing this module, you'll be able to recall the measurement principles of swirl flow meters, list reasons for the use of swirl flow meters, analyze the different application requirements and identify possible measurement principles. Swirl flow meters measure velocity. The internal area of the meters is usually known. This means that volumetric flow can be accurately divided from the velocity measurement. Flow rates in actual volumetric units at the operating pressure and temperature are measured. Mass flow rates or volumetric rates based on standard conditions must be computed from the actual volumetric flow. Principle of operation. The swirler is solid welded and has no moving parts. The same sensor and the same electronics are used as for the Vortex Master flowmeter. The D-swirler is located near the device. It forces the medium back to a well-developed flow profile in order to avoid further pressure drops behind the flow meter. Swirl flow meters also cause oscillation of the medium to determine the flow velocity. In this case, however, the fluid is rotated by a swirler on the inlet side, and a sensor is used to determine the rotating frequency. The inlet guide body causes the axially entering flow to rotate. In the center of this rotation, a swirl core is formed, which, due to the backflow, is forced into a spiral-shaped secondary rotation. Inside this core, the pressure is very low, so that the sensor phases of high pressure and low pressure alternate with the rotation frequency. The frequency of this secondary rotation is proportional to the flow rate and is linear over a wide flow range for optimized internal geometries. This frequency is detected by the same piezo sensor ABB uses for the vortex flow meter. In addition to the shape of the inner geometry, the piezo sensor also plays an important role in the swirl primary signal. Vibrations, hydraulic noise, and pulsation are always present in the pipe and have to be overcome. The flow signal detected by the sensor is therefore not an ideal sine curve, as in the theory. Intelligent sensing algorithms in the electronics have to distinguish between the two elements, the noise and the real flow signal. To achieve this, ABB implemented two compensation piezo elements in the sensor in addition to the two flow piezo elements. The compensation piezo elements measure only the pipe vibration, whereas the flow piezo elements measure the flow signal plus the vibrations. The isolated flow signal is the signal from the flow piezo elements minus the signal from the compensation piezo elements. This makes the system ideally balanced and enables the transmitter to compensate effects from the pipe vibrations. Furthermore, the PT100 is provided for temperature measurement for compensation purposes. The flow signal is often affected by hydraulic noise and vibrations, etc., which need to be filtered out for accurate and reliable flow measurement. Looking over the full spectrum of the frequency range, there are many peaks caused by noise or vibrations. Physically, all swirl flow meters generally measure in the same frequency range and have to overcome the same challenges. Only those with an intelligent signal processing combined with a sensor that provides reliable information can deliver the greatest performance under challenging process conditions. Digital signal processing in combination with the balanced sensor from ABB ensures maximum measurement precision and reliability. Without the intelligent vibration compensation, the meter would pick up the wrong frequency for flow computation. Despite the algorithm mentioned earlier, when there is no flow in the pipe, the meter may pick up a signal which is pure noise. As a manufacturer, ABB tried to make the meter as sensitive as possible to detect the lowest flow rates by setting the factory noise threshold to a low value. If the actual signal magnitude of a certain noise frequency is higher than the threshold, the meter will use this signal to make a flow calculation from it. The auto zero function reviews the signal spectrum for a period of time and adapts the threshold to a new value above the noise magnitude. This could result in a lower overall sensitivity of the device, but helps to have a stable 0 point at no flow condition. Auto zero can be executed and repeated when the conditions change by heart or by the display buttons. The noise threshold can be adapted by hand if necessary. The measuring principle works for all gases, steam and liquids with low to medium viscosities. The independence of conductivity make these meters ideally suitable for all applications of petrochemical raw products, solvents, or boiler feed water. The measurement is independent of the density, temperature, viscosity, and pressure, as long as they are in accordance with the limits of the measuring principle and physical meter specifications. The design of having a sensor unit which is completely separated from the bluff body or swirler unit makes the meter widely insensitive to deposits, pollution, or coating. Because of the principle of measuring the rotation frequency of the medium, the design is very insensitive to misalignment, as overall there are in general low demands for installation in respect of straight and undisturbed up and downstream sections. As you have now learned how this measuring principle works, you can understand why flow meters of this type cannot start working from zero, contrary to electromagnetic or Coriolis mass flow meters, for example. A specific flow velocity is required to build up the internal flow system and be able to reach the linear range. As a result, a low flow cutoff must always be taken into account. The bluff body or swirler constantly causes a pressure loss, which, in the worst case, may create a cavitation in the pipeline. This cavitation is strongly destructive and must be avoided by providing sufficient static overpressure in the pipeline. Two-phase media like paper or sludge and wet steam cannot be measured. Liquids and gases are measured at completely different flow velocities, so a gas-liquid mixture will be measured under incorrect conditions. Minimum pressure. The signal quality is a function of the medium density and flow velocity. The higher the density, the more the signal will be gained, and the better is the signal-to-noise ratio. The requirement of 0.5 kilograms per cubic meter is given in order to meet the full meter range. In hydrogen applications, for example, a minimum pressure of 5 bar gauge or 72.5 psi G respectively is required to meet this limit. If the customer wishes to measure anything other than actual units, the impact of temperature and pressure must be compensated for. Swirl flow meters always measure the actual volume flow of liquids, gases, or steam as the primary signal. This means that one pulse at the sensor always refers to the same specific volume. However, the content of the molecules inside this volume is influenced by temperature and pressure. This influence has to be compensated in some way. Every volume contains a number of molecules which require a certain space. Temperature and pressure do not influence the mass, but do influence the volume because the number of molecules does not change. In liquid measurement, the impact of pressure is typically ignored because ideal liquids are not compressible, whereas gases are. Temperature has an impact on both liquids and gases. The volume typically increases with increasing temperature. In order to compensate these influences, swirl flow meters offer different operating modes. For liquids, with and without density or volume correction. For gases, with temperature compensation only, or with temperature and pressure compensation for standard or mass calculation. For steam, depending on the type of steam, with temperature compensation only for saturated steam, or with temperature and pressure compensation for overheated steam. Modern swirl meters with enhanced computing capability can calculate the energy flow directly from all of this information. For the compensation of the temperature effect, the temperature sensor, which is located directly in the piezoelectric flow sensor, can be used for this purpose. The customer can avoid measuring errors that may result from unfavorable PT100 installations or bad wiring, and does not have to spend time or money on a remote temperature system. The integral temperature measurement can make the swirl flow meter a true two-wire mass flow meter for saturated steam. In combination with a pressure signal from a remotely installed pressure transmitter, a full compensation of pressure and temperature is possible. This will be introduced in the application module in more detail. Now, let's summarize this learning module. What have you learned so far? You can recall the measuring principles of swirl flow meters. You know the key elements of swirl meters: bluff body, piezo sensor and transmitter with intelligent sensing algorithm. You can recognize application features and limits when selecting and sizing swirl flow meters.